I want to talk about Le Chatelier's principle that if you introduce a change such as concentration, pressure, or temperature to a system at equilibrium, the position of equilibrium changes to reduce that stress or change. And for sake of simplicity, I want to look at one example, which is production of methanol. If you take carbon monoxide, a poisonous odorless gas, mix it with hydrogen, usually in presence of some sort of catalyst, you will produce a fuel of choice, methanol, CH3OH, which is also the first member of alcohol family. It's also has the following information: delta H of formation, entropy of formation is minus 202 kilojoule per mole. You should realize immediately if the value of delta H is negative, that means the reaction is exothermic. And it's crucial in order to at least worry about effect of temperature on this. I'm going to write this equation one more time to reinforce that exothermic reactions simply have the quantity of heat on the product side. It exits the system. That's why it's exothermic. CH3OH gas plus quantity of heat, you can write simply heat, or you can write the 202 kilojoules here. Now the first, which is the easiest, let's look at concentration. If concentration of one of the species goes up, the system shifts to other side to reduce that change. So for example, let's just play with concentrations of carbon monoxide. Concentration of carbon monoxide in bracket, if this goes up, if CO goes up, you will shift to the right hand side to reduce that change. So in this case, shifts, and by shifting we are talking about position of equilibrium, shifts toward product. What happens if I increase concentration of methanol? So in case of methanol, CH3OH, if I increase that, if this value goes up, this time you will shift to the reactant sides. So shifts toward reactants. Same concept applies in removing concentration. If you remove one, you will shift toward that component that you removed in order to give it back to life. So in case of methanol, if you want to produce more methanol, if for example concentration of methanol goes down, if you remove it from the system as it's being made, you will shift toward product. You will give more product. Shifts toward product. So if methanol goes down with arrow going down, you will shift that side. Now one thing you should remember, pressure and concentration do not change value of Kc or K. So removing or adding concentration does not affect K. You simply will create a new proportionality. That K is steady and specific at that temperature, given temperature. Now let's look at pressure. So in case of pressure, let's see what happens. Now you should remember your ideal gas law. Pressure applies only to gases, not liquids, solutions, or solids. PV was equal to nRT. It still is the case. Pressure times volume is number of moles times gas constant times temperature. If temperature is constant and number of moles are constant, this whole terms is simply a constant. If that's the case, which is always the case, pressure is inversely proportional to volume. And that's usually where many of my students make mistakes. In this fashion, if volume of the vessel decreases, that means pressure increases. So many times in questions, you might not have the pressure being increased, rather volume is decreased. Same thing is true. If volume of the container increases, that means the pressure of that inside that container is decreasing. Pressure decreases. Now for system at equilibrium, If pressure increases, the system shifts to the side with less number of moles. Then let's just look at methanol example and increase the pressure of the system and see what happens. So carbon monoxide plus hydrogen gas was giving you CH3OH. It was exothermic, but heat has nothing to do with my pressure at this stage. We assume temperature is held constant. Now, what you should realize is these are all gases. So you have 1 mole of carbon monoxide, 2 moles of hydrogen. Collectively, you have 3 moles of reactants. On the right-hand side, on the product side, you simply have 1 mole of product. Now, what happens if pressure increases? If pressure increases, I move to the side with less number of particles, 1 mole. In order to give you more moles, more N, to compensate for the pressure, to bring it back to life. So if pressure increases, shifts toward methanol product. Now what happens if volume increases? If the question is saying the volume of container increases. Now then go back to your PV equal nRT or the relationship. Remember that when volume increases, that means pressure decreases. This means simply shifts toward reactants. Why? Because when volume goes up, that means pressure goes down. And if you memorize one that pressure increases, you shift to the side with less particles. The reverse should be true. If pressure decreases, you shift to the side with more particles, which is reactants. So that's pressure. Now, also, I want you to just remember, if you touch pressure, the value of K does not change. K is not affected. Kc is not affected. The only thing that changes K is temperature. Now let's look at temperature for this exothermic reaction. So the last variable and the most important, let's see what happens to temperature. Now let me write my equation one more time. Carbon monoxide plus hydrogen gas giving us methanol, CH3OH gas plus 220 kilojoules, 202 rather, plus heat. Now heat is a quantity. It's just almost like the same concept as concentration. If it's exothermic, if you increase the temperature, that means the quantity of heat goes up. So for exothermic reaction, then you will shift toward reactants. So you can memorize it. I like you to sort of feel it and see it. If heat temperature is increased for exothermic, you shift toward reactants. So for exo reactions, if temperature increases, position of equilibrium shifts toward reactants. And Kc changes. This is the only time Kc change, because K is function of temperature. Now let's see what is Kc, and would you go up or would you go down? Kc was products, which in this case is methanol, raised to power 1, its coefficient, divided by carbon monoxide multiplied by hydrogen to exponent 2. Now we decided if heat goes up, you shift toward reactants. So that means that concentration of CH3OH permanently goes down, concentration of carbon monoxide goes up, concentration of hydrogen goes up. Simply, your numerator is getting smaller and denominator is getting bigger. So that means Kc decreases, goes down. So for exothermic reactions, if temperature goes up, you shift toward reactant and Kc permanently changes, Kc gets smaller. So what happens the reverse for endothermic reaction? If many of you like to memorize, I know that. So for endo, if temperature increases, you shift towards product, and Kc increases. The last thing I want to touch upon is, what about catalyst? What happens if you have a catalyst? Is that a change that you need to worry about in equilibrium? And I'm saying no. Now let's see what happens to our example. Carbon monoxide plus hydrogen gases. Usually in production of methanol we have zinc oxide or copper oxide as a catalyst to speed up the reaction. So this quantity that I wrote on top of the arrow, it's simply a catalyst. Now let's see what happens when you introduce catalyst to system at equilibrium. Now remember, if your energy diagram, you had energy on y-axis and you have profile of time here. If exothermic, that means reactants are here and products are somewhere here, more stable and lower energy. And this is exothermic reaction. This is your forward reaction and this is your reverse reaction. Now what happens if you introduce a catalyst? You simply offer a new pathway with lower activation energy. So this is activation energy with catalyst. Now if you introduce to a system at equilibrium a catalyst, you will speed up the forward reaction and you will speed up the reverse reaction equally. So a catalyst has no effect on the position or value of Kc. So remember that for sake of answering questions, catalyst has no effect on either the position of equilibrium or the value of Kc. So that's for Le Chatelier principle, who was a French chemist, and he gave the most practical, simple idea of chemistry. Good luck until next time.